Start by finishing the problem that we began during class today. Um, this is where we stopped. We started on problem part A. In this problem, we are talking about the half-life. Half-life will let me predict what my rate of decay is. So on this next page, and this is where we stopped, we have m equal m sub 0, that's the initial amount at time 0, times e to the minus rt. If I divide both sides by my initial amount, I will get the fraction of the quantity that is left at any time t. The half-life tells me when I have half of my substance left, it has taken me 12.36 years. By telling me that, it's going to give me an idea, well, it'll actually allow me to solve for r. So if I take the natural log of both sides, I get ln of a half equals minus r times 12.36, and I divide both sides by 12.36. When you do that, you will find that r, if you were to plug it into your calculator, is approximately 0.56. Nope, try it again. It is 0.056 approximately. So we're going to work with that because what we're doing right now is we are approximating. I don't think we could get much more exact than that. So let's look at this next part of our problem. It says 500 milligrams of potassium 42 are taken. How many milligrams? Ooh, I think I'm missing something. How many milligrams, wow, will remain after 48 hours? Let me make that so we can see that a little bit better here. Let's see, move this over. I don't know how that happened. There we go. If 500 milligrams of potassium 42 are taken, how many milligrams will remain after 48 hours? So basically, we were just taking our model that we developed, m equals m sub 0 times e to the minus r, which we determined was 0.056 approximately, times t. And it's telling me I want to know how much is left after 48 hours. One thing that is very important is this says 48 hours. I better be certain that when I determined the half-life was given to me in hours. Otherwise, I have to do some conversion. And in this case, it was, so we're fine. So we'll go and we'll just strictly plug in. It tells me 500 milligrams were taken. That was my initial amount, 500. Times e to the minus 0.056, and t is 48. And now this becomes a calculator problem. If you plug this into your calculator, you will find that you will have this is approximately 34.01, and that's milligrams. That's the approximate number of milligrams after 48 hours. The next part of our problem, and again, I don't know what happened to me here, but this is all gone off the screen. Hold on. Make that smaller. Let me read it now. Close. Yep. How long will it take for the original 500 milligram sample to decay to a mass of 5 milligrams? So it's telling me the amount that I want to have left. That's 5, and maybe I'll write my equation up here, my formula. Okay, so 5 is the amount that I'm going to have after I've had some decaying going on. My initial amount is 500. e to the minus r, and we determined that was approximately 0.056 t. So we're going to solve for t. We'll divide both sides by 500. That gives me 1 over 100 equals e to the minus 0.056 t. At this point, we're going to take the natural log of both sides. ln of 1 over 100 equals negative 0.056 t. And we'll divide both sides by negative 0.56. ln of 1 over 100. Ooh, not writing very well there. Let's see, we'll undo that. I want it to look more like 100. Okay, here we go. T equals ln of 1 over 100 divided by negative 0.056. When I plug this into my calculator, I will find that T is approximately 82 hours. So after 82 hours, I would expect to have 5 milligrams left. Now, here is another model. Loans are paid in equal payments consisting of the principal plus the total interest divided by the total number of periods over the life of the loan, N. The periodic payment R is given by this formula here. A lot of times we want to know how much longer it will take us to pay off a loan. So we can find the time in years it will take to pay off the loan as a function of the periodic payment by solving for T. So I thought we'd do that. Let's see, I'm going to extend this page a little bit. Okay, so in order to solve for T, the very first thing I'm going to want to do is I'm going to just move the P to my numerator there. So that's R equals P times I all over 1 minus 1 plus I to the minus nt. Now, I want to define some things a little bit there. P is principal, that's the amount of my loan. N is years. T, N is not years. Hold on a second. I believe N is compounding periods. Let's go back and look just a second. Number of periods over the life of the loan, N. N is compounding periods. What else? Time is time in years. I is your annual rate divided by the number of compounding periods. And R is the payment. Okay, so let's solve this for T. I am going to multiply both sides by my denominator so I can get rid of my fraction. That would be R times the quantity, 1 minus the quantity, 1 plus I to the minus nt, to the minus nt, equals P times I. Now, again, I want to solve for T. So I'm going to distribute the R. That would be R minus R times 1 plus I to the minus nt equals Pi. Oh, I think I'm going to go a little bit of a different direction. Rather than multiplying that through, I think I'm going to divide both sides by r. I think it will be easier in the end. What I did was not wrong, it just might take me longer. So I'm going to divide both sides by r. That gives me 1 minus 1 plus I to the minus nt equals pi all over r. Next, I'm continuing to want to isolate t, so I'm going to subtract 1 from both sides. Next, I'm going to divide both sides by negative 1. And when that happens, I don't like this dot there, because doesn't that look like an I? This is, I subtracted 1 from both sides. I'm going to divide by negative 1, so that's minus pi over r plus 1. Now, I want to get this out of my exponent. I have no idea what this base is, so I'm going to take the natural log of both sides. When I do that, well, I guess I'll write more than one step. 1 plus I to the minus nt equals the natural log, I'm going to reverse the order here, 1 minus pi over r. Okay, now, by taking the natural log of both sides, I'm allowed now to take the minus nt out and put it in the front, because that was my exponent. That's one of the logarithm properties. And now, to get t alone, I'm going to divide by minus n ln of 1 plus I. And there you have it. That's the length of time it will take me to pay off the loan with principal P, my initial loan amount P, and R being my payments, where I is the annual rate divided by the number of compounding periods, and N is the number of compounding periods. So there you have it. Very nice, right? Now, when I took the natural log of both sides, I really could have done any log. I could have done log base 10, I could have done log base 5, any log, but natural log is awfully nice because it's one of the buttons we can use in our calculator. Now, this next problem asks me how long it will take James to pay off his loan if he makes $200 per month payments. And at this point, we're just plugging in. Now, I'm not going to make you memorize this formula. I don't have it memorized. So if I were to ask you to use this formula, I would give it to you. So how long will it take? Well, t equals, now let's just start identifying some things. 15,000 is P. That's his loan amount. The annual rate is 0.13 compounded monthly. So I is 0.13 divided by 12, which is the number of compounding periods. I'll write that in there too because we need n. N is 12. And my payment, R, is equal to $200 per month. So now at this point I can just plug in. I kind of don't like where that is because I'm running out of some room here. Let's see. It's pretty good. So t equals the natural log of 1 minus, I am definitely running out of room. Let's move this around a little bit. And group this and make it smaller. There we go, I'll have room now. So the natural log of 1 minus p, which is 15,000, times I, which is 0.13 over 12, all over my payment, which is R, 200, divided by minus n, the number of compounding periods, times ln of 1 plus I, 0.13 over 12. Okay, and then that's just a calculator problem. It's ugly, but you know, that happens sometimes. If you plug in, you will find that T is 12.94. It will take 13 years to pay off that loan. Okay? Next, here is the population P of a city. It's 105,300 times E to the 0.015T, where T is equals 0 represents the year 2000. According to this model, when will the population reach 275,000? Press pause. Try to do this problem. When you're ready, press play and check your answer. And here you go. So I set P, the population, to 275,000, and I solved for T. And you can see that I got T equals 63.997. That is 63.997 years after the year 2000. So it will hit that population in the year 2064. Next, logistic model, growth model. Some populations have rapid growth initially, and then then declining growth or more constant growth. This can be modeled as a logistic curve. A and B are real numbers. R is a real number. Y represents the population size, and X represents time. This can be used when you are modeling conservation biology, a learning curve, spread of a virus on an island, carrying capacity. So here is an example. The number of iPhones purchased is given by this equation, and you'll notice it's logistic. I am not going to make you memorize this formula. If I wanted you to use it, I would give it to you, where T is the time in weeks after they are made available. How many iPhones are purchased within the first 2 weeks, within the first month? So we will just plug in. N is the number of iPhones. Ooh, there we go. That's equal to 2 million all over 1 plus 2 e to the minus 4 times 2. Again, it's really important to make sure that you have your units right. Time in weeks, 2 weeks. Okay? So if you plug this into your calculator, you will find that, let's see, it is 1,998,000. Oops, something's going on here. 659. Now, within the first month, remember we need the same units. So we're going to say a month is 4 weeks, and we'll plug in again. And again, it becomes a calculator problem. 1,999,999.55. And that's all there is to it. Logarithmic model. Sometimes logarithmic models are used to model population of species, anesthesia wearing off, time to pay credit cards. Now, I'm not going to do an example of this, but what I want you to realize is that all of these problems follow this same general pattern. I'm going to write down what that is. The same general pattern. First, they tell you the model they use. As soon as that happens, you write the equation. Next, they'll tell you some points in time. They'll give you some data points. You should plug these values in. And solve for missing parameters. The missing parameters are the real values that are given in the model. So you'll have to take the data points and solve for it. So for example, if I was looking at this logarithmic model, I would be given some data points. I would plug in, I'd have to be given 2, and I'd plug in and solve a system so that I know what A and B is. After that, you rewrite the equation in number 1 with the values you found from number 2. And then finally, you make predictions. From the formula you found in step 3. All of them follow that basic pattern. So that's all I have for you today. Your homework is on my website. I will see you tomorrow.